There we go.
And I'll start sharing screen.
Yeah.
So I was gonna go over the project first and then dive into the lecture, but maybe I should switch up the order. Okay, so yeah, I'll treat this like a recorded one. For those who are here, don't hesitate to ask any questions or even unmute or anything like that. Um, but yeah, I'll just kind of go through it maybe at a slightly slower pace to mirror what a purely recorded lecture looks like. So today we're going to be talking about speed and security trade-offs in blockchain protocols. And this is important as developers because ultimately when you decide to build on a blockchain, you are making a decision to endorse a certain protocol and a certain community um, with your code, with your attention, with your participation, whatever it may be, all of the above. So right now, most people who build blockchain apps at a production level build on Ethereum. And today, I'm going to basically try to give some of the intuition as for why Ethereum is the safest option right now to build a long lasting, secure application. So, yeah, now that a couple more people are joining, um, as I was saying, the intuition that we're going to go over in this lecture may be a little bit dense, but hopefully it clears up why Ethereum is the blockchain of choice for most blockchain developers today. And hopefully from this lecture, you can go on to select your own blockchain if you want to build on something else like Solana or um, anything, Algorand or any of these other blockchains. You can understand why Ethereum is so popular and have some more clarity in your decision. So, yeah, great. Let's get into it. This is an adaptation of a white paper deep dive that I hosted with Bab. Um, and what we used to do is go over a paper every week. So this is one of the papers that we went through. And these are the sections I'll be talking about. So starting off with why even read this paper. This paper being a paper titled Speed Security Trade-Offs in Blockchain Protocols. So if you want to follow along with me, you can just enter that into your search bar, and the first two results should be the same paper. Um, so I think this paper is very interesting because it demonstrates three foundational things of this industry. One is understanding why people respect proof of work based blockchains so much, namely Bitcoin. Second, it demonstrates the need for consensus mechanisms and actually tells you where in the protocol stack a consensus mechanism lies. And finally, because it gives you a good intuition on system level security in terms of how many adversaries can you handle in a blockchain system. And these are all very important things to consider when you are building for blockchains. So, first, some background. When I read this paper, it is actually an extension of a paper that's based on this foundational paper, the Bitcoin Backbone Protocol Analysis and Applications. And this is a very good 40-page paper kind of outlining the Bitcoin Backbone Protocol. And it's a very fresh way to look at blockchains. Um, what's cool about this paper is that it has a a way to break down the Bitcoin protocol into external functions. So it basically focuses on the Byzantine agreement problem. Does the Bitcoin blockchain achieve Byzantine agreement? And ultimately, what it argues is that by itself, Nakamoto's white paper falls short of Byzantine agreement, which is a super interesting fact because in this space, the people who you will talk to, the first thing that they'll tell you is the Byzantine general's problem is solved by blockchain. But that's not entirely true. Um, Byzantine agreement is achieved only after you build applications on top of the protocol. So the core backbone, which is the proof of work protocol, that doesn't by itself guarantee Byzantine agreement. You need the external validation, input, and reading functions on top of that protocol to create a system that achieves Byzantine agreement applications. Um, and ultimately, the main problem that is solved with Byzantine agreement is double spending. So if the person who is paying, if you go to the store and try to buy a coffee using Bitcoin, you would have to wait K blocks before receiving your coffee. And the reason for this is because after K blocks are added to the network, the probability that an attacker can reconstruct the chain drops exponentially by K. Meaning it's very unlikely that if you wait 30 minutes and the it's very unlikely that the next block is going to be on a completely different chain. Um, because if you remember in Bitcoin, all the miners don't exactly have the same copy of the chain at the same time. They have, and we'll dive into this later, but they have kind of a property that says most of the chain is the same, but the last like 2 to 3 blocks may be different, and that's okay. So yeah, diving more into Byzantine agreement. Basically, there's two main properties outlined in the paper for Byzantine agreement. The first is the agreement property, in which there is a round after which all the honest parties return the same output if they are queried by a user or the environment or whatnot. And that kind of relates to the distributed systems cap theorem. So the second property is validity, that the output returned by an honest party P is the input of some party P star that is honest at the round where P made the output. So that's all that is saying, is that whatever honest party P, their output is the same thing as some other honest party's input on the round where P's output was produced. So this kind of is a blanket idea of Byzantine agreement. And today we'll kind of dive into how proof of work based blockchains can support Byzantine agreement. And feel free to be asking any questions along the way. If you don't understand the nitty gritty of this stuff, that's okay. Yeah, that's this lecture is more to demonstrate the intuition behind proof of work. So more definitions. The common prefix property is what I referred to earlier, and it essentially means that all chains that honest miners are working on share a common prefix. So let's say that you have 3 miners, all 3 of them are honest. They might not be working on the same transactions in the same exact order because each respective miner's mempool could be different. So what we can't agree that down to the last block, all of their working chains are the same. But what we can agree on is that if you cut off K of these blocks from the tip of their chain, so you prune it, there is a strong common prefix once you prune the tip of all their chains. So let's say we take off the first 2 blocks out of all of these chains. There is a pretty high probability that now all of these 3 chains are the exact same. And that's what kind of makes a blockchain. How do miners choose which transactions to take from the mempool? There are a variety of ways they can do it. The highest way is basically just the transaction fee, depending on the blockchain you're using. So in Ethereum, it's often the gas fee, which determines how fast your transaction is processed by the network. The second property is chain quality. So the chains that honest miners agree upon, the idea is that they should be pure. They don't have long strings of adversarial blocks. And long strings of adversarial blocks usually imply that the chain was attacked somehow. Some double spend attack, some race condition, some sort of attack allowed an adversary to basically make his own chain and then beat the other chains out and then make a double spend that way. The final property is chain growth. So the idea here is that the chain will keep on growing by some bounded coefficient and new transactions will always be included. Not all blockchains actually have this property. Some blockchains, like the XRP blockchain, for example, has an inbuilt freeze mechanism where if certain conditions are met, certain fault tolerance conditions are met, then the blockchain just freezes progress. These are good for some use cases. Um, it's honestly undefined right now what they are useful for, but it's cool technologically. Great. So we're essentially in this paper going to prove a good model for the common prefix property, and that's essentially what we're going to try to do right now. And why are we doing that? Because we want to demonstrate how Ethereum, Bitcoin, and some of these blockchains are provably secure using the assumptions on this slide. And we'll walk through the proof of this and build the intuition that way. So let's kind of build our scene here. Let's say that we have a set of n miners, and this basically includes the entire hashing power of our system. And out of those n miners, t of which are adversaries. And let's assume that the communication happening between these folks are synchronous, meaning they're saying hi or sending messages over a live network. So, given n miners, t of which are adversaries, how do we determine security parameters? There's a couple things we have to look at. First is the concept of a round. So in this paper, we call a round an instance of full propagation in the network, where if a single miner broadcasts a transaction, a round is the time it takes for every single miner to receive that transaction, receive that broadcast. So statistically, this boils down to around 12.6 seconds on average. The reason it is so fast is actually beautiful. Bitcoin has its own version of a gossip protocol, which ensures that any message can be sent to any other miner in the whole world by only 3 hops because of mutual peering. So it really only actually takes 12.6 seconds to deliver a full network propagation message. So that's very cool. And going more on that point, actually, it's really beautiful because these are the things that you have to build on top of proof of work to create a fully Byzantine fault tolerant system. You have to have a networking layer. You have to have validation and all these things that happen asynchronously for Byzantine agreement to be met. But anyways, F for us is going to be basically the total hashing power. So it's the probability of a successful proof of work calculation by an honest party in a given round. So F is really the parameter that we're going to look at today. And you can think of it as a ratio of propagation time to block time. So in one round, how many blocks are made? And as a side assumption, in the real world, miners have varying levels of power. Like if I were to mine Bitcoin on my laptop, that would have a completely different effect than mining on a GPU rig or an ASIC rig. So we kind of account for this with the concept of n miners having equal hash power. And if you wanted to simulate having different levels, different buckets of power, you can just group some subsets of n together and have those be like your powerful miners. But in both scenarios, n is the total hashing power, the total number of people. And we kind of assume that we only make q hashing queries per round. So the throughput of each of these n miners is the same. And ultimately, this is only for the proof to work out. Great. So why do we care about any of this background? Is because these are parameters that are actually very important in the debate for things like the Bitcoin block size, for ETH 2.0, hype. Block size determines how many transactions are included in a block. And the current 1 megabyte limit has been up for debate. There have been proposals for like a 20-fold increase. But the paper argues that when you scale a block size, the round scales by the same constant because it takes more time to deliver larger messages. So therefore, the TPS, the transaction per second or transaction processing speed, doesn't change that much. And Bitcoin actually calibrates the hardness of proof of work um, to maintain a block time of around 10 minutes. And Ethereum does the same thing for a shorter time, for 12 seconds, I believe. So this prevents it's to prevent DDoS attacks, to prevent a flooding of messages in the network because you have to wait for the next block. So the underlying equation down there is very important. It is our TPS is proportional to the block size times F over the round duration. And remember, F is basically the probability that a block is honest. So, yeah, the block size times the probability that the block is honest basically means blocks per round. So cool. This is the first big money shot of this presentation, which is kind of going over a lot of the things that we talked about. So there's a bunch of altcoins on here. These are all proof of work based coins. So nowadays with proof of stake, there really is no concrete literature on measuring the same things because we haven't seen proof of stake operate with the volume and scale of Ethereum or Bitcoin. But when comparing proof of work blockchains, Bitcoin's block time in the first column is very slow compared to the others, and that gives it a lower number of blocks per round. But ultimately, and ultimately that means that the number of rounds that are expected to get a new block is very high. So Bitcoin expects almost 48 instances of full network propagation. So you can think of that as like the miners have to talk to each other that long in order to get a new block out. And for Ethereum, it's a lot shorter, but we'll discuss and look at how that affects the actual final balance for security. But this is really cool. I mean, you can think of these networks as legitimately live organisms and systems with people behind them. They're not just like random programs that exist for, and these numbers are not just arbitrarily given for fun. It's actually really interesting why the Bitcoin developers have decided to make this block time so long, such that there is a debate over where the next block comes from. There is multiple rounds of network propagation, broadcasting messages talking about what the next block is, verifying the next block before it actually enters the blockchain. And that level of security is still unmatched in the blockchain industry. All these people are trying to move to proof of stake because it's faster. Everyone wants lower gas fees to work on DeFi. But oftentimes people forget that the reason this industry exists is because of the security that we get from proof of work based algorithms. So don't forget that. So the ultimate question that we're asking is, for a given block generation rate f, what is the maximum adversarial hashing power that can be provably tolerated by a population of honest miners? So we're looking for a percentage here. If you have a blockchain, what percent of the miners can be adversarial for your blockchain to still work properly? That's the question we're asking. Fair warning, it's about to get a little more complicated. Stick with me for the next couple slides, and I'll tell you when you can zone out because there's one part that is a bit tough. But going into the actual paper, we just covered kind of the introduction and set the scene for everything. Now we'll talk about the chain growth property and the common prefix property. So let's dive in. And quickly, if there's any questions, feel free to unmute or hit the chat or anything. Even if you want me to summarize the entire thing so far, that's totally fine. I might do that anyway. Cool. So kind of moving on. The numbers on the screen, the symbols on the screen are basically all probabilities of a block being honest. So you are familiar with the way that proof of work mining works. You do a bunch of hashes and you compute a hash value that is smaller than a certain parameter d. So that's why proof of work mining is hard, because you can't predict the hash function's output. So you have to keep trying random things until you hit a output that is lower than d. And that actually is the proof of work algorithm. So it's a lot less complicated than people think it is, but that's good because we can actually put that into a mathematical equation and use it in a proof. So the probability that we get a successful proof of work is d over 2 to the k, where k there is our like bit space. Yeah, length of the hash. So knowing that, we can say that alpha, which is the hashing power of honest players, is the probability of a good block times the number of queries times the honest miners. So if honest miners make q hashes with the probability of p, then alpha is, that gets alpha, which is the hashing power of the honest players. So we can just abstract that. The same thing applies for beta, which is the hashing power of the adversaries. So F is the total hashing power, which is alpha plus beta, is the total probability of a block, honest block. So going forward, we have a common prefix. And this property is ultimately what creates a robust blockchain. So let's say that two honest miners have the same view of the chain if they prune blocks from the end. That is the definition of the common prefix. So go ahead and look at this graph. On this graph, there are three miners, and there's M1, M2, and M3. M1 has a certain blockchain from X1 to X3. M2 has X1 to X3. M3 has X3 and has like a Z4 here. This is actually legitimately how it happens in real Bitcoin, like in real Ethereum. The blocks at the end of the chain are not necessarily the same for every single miner, but if we prune two blocks from the end of all of these chains, then we can guarantee that at least the first three are the same. And that is the common prefix property. This chain, x1, x2, x3, is mathematically guaranteed to be the same. Or M1, M2, and M3 are all guaranteed to share the common prefix of x1, x2, x3. And that is blockchain. That is literally like, if there's anything that sets you as a blockchain enthusiast or learner apart from the 99% of other people in this industry, it is this common prefix property. The understanding that these systems take time to come to consensus, even more than just the block time. So it's about a bunch of different autonomous machines communicating and coming to agreement on something. It isn't as, so yeah, it's not just like set in stone the minute that a block comes up. It's pretty cool. It's like almost like a live organism, like a live network. So yes. So if, yeah, and that's cool. If the ratio of adversaries is below 1, like there's like not that many adversaries, and we can assume that there's a large common prefix. So yeah, I'll explain hashing power again. So what hashing power essentially is like, the simplest way to think about it is how much electricity are you using, almost. So like, if you think of me running my node on my laptop, I have the hashing power of that my laptop can put out. Hash power is like compute power, essentially. It's compute power times the probability of a good hash times the number of queries that you can make. So hashing power depends on like your network's connection speed and your network connection speed to other peers, as well as your actual computing power that computes the hashes. So basically, it correlates with your compute power. So I would have less hashing power than like a warehouse of GPUs. But yeah, so that's the common prefix property. And the next property is chain quality. So honest miners' chains do not contain long sequences of adversarial blocks. If a chain contains a long sequence of adversarial blocks, that usually implies that the chain was attacked somehow. So some kind of double span Sybil attack happened on the chain because there is a series of blocks that don't belong there, and everyone was fooled into thinking that they belong there. So if the ratio of adversarial to honest blocks is bounded by t over n minus e, is it e to the t or e times t? Yeah. Then there is a strategy under favorable network conditions for the adversary. And all this is really saying is that under the same assumptions that we made earlier, we can guarantee some sort of quality in once we prune the chain if the system has a majority of honest miners. So that is the two properties that we need basically to have a secure chain. And this paper, what it's proving is that we can achieve we can prove that these two properties exist by using good bounds. So the GKL paper proved that these properties exist using the bounds you see on the top there. So gamma u, the probability that a round is successful, is greater than that coefficient based on f times b, which is the adversarial hashing power. And what this paper is proving is that you don't actually need a coefficient based on f. We can prove directly that the probability bound of a successful or uniquely successful round is just greater than the adversarial hashing power on face. So that's actually a huge improvement in security bounds. So if you see on the right, the graph here, Ethereum has almost one round per block. Like the expected number of rounds for one block is one. Flashcoin is like an altcoin that has less. And the curves that you see are the security bounds. So in Ethereum, this curve on the GKL bound is saying that at a block time of one round per block, Ethereum could not handle any adversarial behavior, which is incorrect because in practice, we've seen Ethereum handle adversarial behavior at this block time. So something doesn't add up here. This paper goes farther to say that in the green line, Ethereum can handle 35% of adversarial hashing power by taking out this coefficient. So what we're going to do next is walk through the proof of the common prefix property using the new bound instead of the old GKL bound. And this is a dense part of the paper, which I think could be explained or could be better digested by actually reading the paper, but we can go through the beginning of it. So this is a proof. This uses concepts from discrete math and probability. So we'll just speed through it, honestly. So the way that they did it is first looking at two types of rounds. First is the successful round, where at least one honest player computes a solution, and that's x. So the random variable x of I means that at round I, the outcome was x. Yes or no, that the round was successful. The random variable y does the same thing, except it's for a uniquely successful round where only one honest player computes a solution in round I. So these are the two random variables that denote whether a round is successful or uniquely successful or unsuccessful if they're both 0. Thus, if a round is and as I said before, the miners have different length chains. So now there's a concept of if two honest miners have different stuff on their chain, what if one is longer than the other? The way that this proof gets around that is by establishing a constant m. So if a round is m uniform, it means that any two honest chains have a difference that is greater than or equal to m. So you can think of the base of a chain, the base of R in a certain round. So base of R, base of a round, is the length of the shortest chain of all miners at round R. So if we wanted to use a stepwise function to calculate the length of the chain, or the length of the shortest chain at the next round, it would be the current shortest chain plus either the round where there was a uniquely successful round, or the M if it was an M uniform round. And that is because a uniquely successful round is good for honest people because everyone has to agree on that one thing. So if that is the biggest, if that is the longest chain, everyone will go to that chain. If it is not a uniquely successful round, then it might be an M uniform round, meaning that whichever one has the longer chain will probably be accepted. That is kind of the Bitcoin idea of longest chain. Put into math here, kind of simplified. So let's chug along towards a proof of common prefix. The adversary must compensate for all uniquely successful rounds independently of uniformity. This is important to prove along the way because uniquely successful rounds are kind of what create a secure distributed system and allow for this favorable bound instead of the GKL bound. So if R is a uniquely successful round that is M uniform with S less than R, then if the M is bigger than 1, there exists a chain C such that at the positions base of R to M, there are adversarial blocks. So what this is saying is that for the adversary to have mined the last M blocks, to have basically fooled all of the honest miners, they would have had to compensate for a uniquely successful round. So if M equals 0, meaning a uniquely successful round or a non-M uniform round, at the end of the round R, for all pairs of honest parties that diverge at a certain round, there exists an adversarial block in one of the two chains right after the base. So that is used in this proof here. So if the round is M uniform, then the chain of length base R plus M must exist. However, at the start of the round, the honest miners have only mined chains of at most base R. Because remember the stepwise formula we had earlier, where down here, if base R plus 1 is at most base R plus the max of these. So if it's an M uniform round, meaning then a chain of length base R plus M must exist. So if the round is uniform, then we consider two chains that diverged at S. And if they were both honest at base R plus 1, then there wouldn't have been a fork because they would have had the same block. So if it forked, that means one of the blocks at base R plus 1 was mined by an adversary. So all of this is just to say that these two chains imply that the adversary has broadcasted distinct blocks at specific locations on adversarial chains. And that is important because that is the fundamental condition for an adversary to have done a double spend attack. Let me go back. That condition that the adversary must have broadcasted distinct blocks at specific locations on adversarial chains. So going forward, now we introduce the gamma bound, which is the probability of an honest block. So for some real delta between 0 and 1, the gamma bound is the coefficient times the adversarial hashing power beta. So let S be the set of chains that honest parties have at the beginning of the round, and the probability S does not satisfy the common prefix property with parameter k in that E natural equation. So that equation, if it looks familiar to you, it comes from the Chernoff bound on the random variable y, which I didn't include in this proof. But we're going to kind of take this as fact that assume that gamma for some real delta value gives you the probability S defined as through k. So this figure, e to the minus omega delta cube k, is essentially the probability that the set of chains does not satisfy common prefix with k. And notice how the probability decreases as k increases. So now that we've modeled the common prefix property, we're essentially going to try to get that value that we modeled on this slide using the new bound that we've created. So this is the property, strong common prefix. The strong common prefix property Q of CP with parameter k states that the chains C1 and C2 reported by two not necessarily distinct honest parties at rounds R1 and R2 are such that C1 pruned by k is a prefix of C2. That's what that notation means. So there's a couple cases. In the first case, if R1 equals R2, this resolves as the last theorem because all chains would share the same set. If it's the same round, they have the same set of chains, so the probability would naturally, using the turnoff bound, equal S. Assuming that R2 is greater than R1, then without loss of generality, of course, then there are two cases that come from here. The first is that the first chain extends C1, and this would mean that theorem 9 applies again because theorem 9, I believe, accounts for S is a set of chains that honest parties have adopted. So there's nothing really special here, but in case 2 is where you have a third chain that comes in the mix. So P1 has a chain C3 adopted in between R1 and R2. So if C3 does not share with C2, then case 1 applies. If C3 does share with C2, this implies that C1 doesn't share with C3 with probability from theorem 9. So C1, C2, and C3 are all in the set S from theorem 9. So overwhelmingly, C1 does share with C3, meaning that theorem 9 applies again. So if you use the union bound on these cases, the probability that there is no common prefix is at most e to the minus omega delta cubed times k, which is exponentially decreasing with k, which is what we stated intuitively in the beginning. So, what does that mean? Bitcoin and other proof of work blockchains are persistent, that if a transaction is seen deep enough in the blockchain, it'll stay there. This is not something you can mathematically prove with other blockchains right now. Proof of work chains are the only really mathematically proven secure blockchains that uphold the common prefix and chain quality properties. Like, I'm sure that once ETH2 comes out and once proof of stake blockchains become more popular, there will be more literature on this. But the way that we calculated this proof was assuming that the probability of an honest block depends on hashing power, that depends on a certain bit space, that depends on a set of miners. Whereas in proof of stake, those assumptions slightly change because your probability depends on how much stake you have. But we don't know the economic people level behaviors of how much stake people will have. So it's really hard to make the same assumptions here. But this is a debated thing, so don't just take my word for it. So this is as long as the common prefix property holds. So how much adversarial power can these proof of work chains tolerate before this property breaks? If the common prefix property breaks, there is no point to using a blockchain. There is 0 point. So now we can go to the graphs. So this is a cool graph. The same plot that we looked at earlier with Ethereum and Litecoin, we now have Dogecoin, which is going to the moon, and Litecoin and Bitcoin. So Bitcoin has the expected number of rounds per block is 47. So if you look on the x-axis, Bitcoin, this is not to scale. Like Bitcoin's hash power for the adversary, it can take almost more than 50% hash power because it goes so slow. So for me, this paper pretty much only proves that Bitcoin is the most secure blockchain on the planet, much more than Ethereum. So this paper kind of made me a little bit of a Bitcoin enthusiast. I was going to say maxi, but I was chill. All right. So yeah. And then the chain growth property also applies here too. So we should go over it. For any chain that is s rounds apart, their difference in length is t times s, where t is the chain speed coefficient. all this is really saying is that distributed systems need liveness, which is an equally important security feature. There's a lot of attacks that can happen if the system like goes offline or freezes. So yeah, there's a 51% attack. So above the curve, there's a 1% chance of a fork that is 100 blocks deep. So the way that this could work is that an adversary rushes to push blocks that keep a fork running by lengthening a forked chain. And yeah, it does some networking layer stuff to keep parties split up. And then that means that randomly resolving ties won't work because it'll always randomly resolve to the adversarial chain. So if you looked at this graphically, it would basically be like one chain coming in, and then a fork happens, and then the longest chain out of the fork chains is the adversarial chain. And then you have to be very lucky for this to happen, but the longest chain gets eventually moved back into the main chain because everyone agrees on it. But it takes protocol level manipulation and it takes networking layer manipulation. So Bitcoin at this point is pretty robust in both of those things, where this would be almost impossible, but still theoretically discussed. So ultimately, some results are that these are the percentage values that we were looking for earlier of how much each of these blockchains can tolerate. So Ethereum can tolerate, according to this paper, 35% adversarial power. Dogecoin, Litecoin around 47% because they're basically forks of Bitcoin. Flashcoin, which I don't even think people talk about anymore, is just trash. And Bitcoin is 49%. So go Bitcoin. ETH does just fine for its purpose at 35. But now I feel like this hopefully sheds some light to like the differences between Bitcoin and Ethereum, different philosophies that people had when making these two chains, and also why Ethereum is the blockchain of choice right now. Because other chains that don't use proof of work, no one really knows the security landscape of these chains as well as we know proof of work. So it is a much higher risk if you're trying to build a startup, like a multi-million-dollar startup. You wouldn't do it on some random chain that uses a brand new novel consensus mechanism. Like you trust proof of work. The community trusts proof of work. So what does this mean? What is the trade-off? It's all about F, the number of blocks per round. So if F goes towards 0, the tolerance for adversarial hashing goes to about like 50 almost. And if F goes to 1, the tolerance for adversarial hashing goes to about 0. So F is the key parameter that scales TPS because it doesn't change the network propagation. So the intuition is that harder consensus means longer block time, means more security in terms of adversarial tolerance. Of course, security is such a large term that there is many different attacks and many different layers to it. So this is by no means a blanket statement, but in terms of percent adversarial power that you can handle, harder consensus means longer block time means more security. So conclusions is that for speed trade-offs, some things that's good is that because of the probability analysis presented in this paper, I feel like we can trust Bitcoin for the most part. It's the most trustworthy blockchain in terms of security. Second, we've proven in a black box that proof of work works as a public ledger, and with the common prefix property, the chain growth property, and the chain quality property. And finally, we've shown that altcoins are actually feasible. They're not, yeah, so they're kind of shutting down the maxi argument. And then finally, this paper did have a number of strong assumptions, just like the static number of parties and full network propagation taking only 12.6 seconds, and even achieving full network propagation in the first place. So there could be some more real life testing. Second is that there is still a gray area in terms of like network level attacks that can happen. We only really touched on like Byzantine fault tolerance, which is the big galaxy brain type problem, but now there's like more minute issues like different attacks that you can do on a network layer. And then finally, we didn't even touch the privacy aspect of blockchain really, because this was so focused on the backbone ledger protocol. But that's okay. Always room for more reading. I hope this sparked some level of curiosity or anything like that. Um, Feel free to ask any questions. We can discuss a little bit until like 7, and then I'll go over the project quickly, and then we can call it. Okay, so confused about merging multiple chains into the main chain through prefixes. I thought Bitcoin's block time was 10 minutes, so what's the probability that unmerged chains have more than one block? I see what you're saying. Okay, so good question. I'll go back to that slide. Ultimately, when you have this concept of, yeah, so same pick. So when you have the concept of like different chains, um, the block time is 10 minutes, but what that essentially means, it means like the blocks come every 10 minutes in the most simple form of the word. But what that actually means is that the miners agree on a block every 10 minutes. But agreeing on a block doesn't just mean you add it to the chain, it means that you actually agree on the chain to move forward with. So that's when merging of chains happens. The idea is that the prefix is the only thing that matters, and there is one common prefix. So not prefixes. There is one common prefix that all the miners share, which is the blockchain. Like that's what the block. When people say the blockchain, they're talking about that. What's happening before you reach that common prefix layer, like before you're k blocks deep, is you're just living on some miner's chains. So and the block X4 in this example lives on both M1 and M2. So it's very likely that X4 will be included in whatever, like the common prefix. Um, so the merging of chains happens all the time, basically. Like there really is no merging of chains, like officially. It's just that as more blocks are added, people just tend to agree on the blocks that are deeper because of the probabilities of the blocks persisting. And the you can think of it like this too, right? Like if there's n people, there's n miners, let's say like 90% of them have the block. So if you're a part of the 10% that doesn't have the block, the only reason why we have this common prefix property is so that the 10% doesn't ruin the rest of the 90%. So just because you have the wrong block in your chain means that it doesn't matter. You can just adopt the longest chain. So your prefix will still be safe. So it's like a security measure. If you want to read exactly what happens, there are good articles on it online. Yeah, but appreciate it. Yeah, thank you for the question. Yeah, I can take any other questions too. Want to talk about anything related to this stuff. I can also talk. This is the last lecture, so I was debating between going over this versus going over like a survey of different cool projects in the space because I know y'all probably want to build some stuff. So I'm happy to do that as well. I can go over some good starting points to do dev. Yeah, I wasn't entirely sure, but I think this is good. Okay, I'm gonna go over the project now. Last call for questions. Okay, I am going the project. So GitHub. So okay, so this is the project. This is the first semester that we are trying this. So what we did is that me and two other Blockchain at Berkeley members, Joe and Ryan, created this NFT marketplace idea. Not actually what it like. This is not really an NFT marketplace. It's just an NFT token, and we implemented buy and sell using direct listing instead of using like an actual three like X way marketplace. Um, I think this is funny because we came up with the idea for an OSCI NFT almost a year ago, and then like 2 months ago, NFTs became so hype that everybody and their mother wants an NFT issued in their name and their face. So it's just kind of funny. I don't know. I, before 3 months ago, NFTs were just like they were just a little simple ERC 721 like interface. No one really paid too much attention to them. They had some novel use cases, but it was not really a big deal. And then something happened. I think maybe NBA Top Shot happened or something happened, and now everybody's on this wave, and it's a little bit uncomfortable, but it's okay. It'll pass, and the real developers will come back and build cool stuff on it. But basically, we have this project for you. Again, this is the first year that we're doing this, so I imagine there'll be some bugs. So be a little patient. I'll keep maintaining the code on GitHub so you can keep checking back and pulling stuff. Um, the original plan was to have you basically um, fill in the blank for the smart contract and the Web3 integration and some of the front end too. While making this project, we realized that it took us collectively quite a bit of time to finish completing this project. So we took out the front end parts, and the only part for the front end is to look at the code and explain line by line what is happening. But for the back end, you actually get to write and compile and test the smart contract and deploy it on a local Ganache chain. So let's go through the code a little bit. This is not the solutions. This is just the normal project code. We will have office hours, so be on the lookout for that. It's only the 22nd of April right now, so it's not a huge deal. But we will have them very soon. Ask on Piazza as well. I'll be monitoring that. So this is a Truffle React unbox. So I made this using Truffle React box. You start off with first the contracts. So this is where all the contracts are. Owned and migrations comes from the truffle box. Owned is something we just use to keep state for owned. Merge token.sol is the thing you'll be doing. So let's quickly walk through the contract. Basically, it's an ERC 721 that's ownable. Yeah, these are all characters. These are different tags and merge types that can happen. So these are all things that OSCI requested. Merge info is kept in a struct. So this is what you use in the front end to get the data. This mapping from uint to merge info, these structs here, this is basically a mapping of the tokens that exist in the contract. So the contract is keeping track of what tokens exist. The next token ID to be issued, every time a token is minted, index increases by 1. So this is how you index into, or this is what constitutes a token ID. Yeah, the constructor for the contract means that no tokens exist, index is 0. This is the mint token function. You will look through this yourself. You will implement this hashing circus. So that'll be fun to do, just some Solidity coding. You have to make sure that the contract understands a token was made. Look through the buy token function, look through all these functions. This is very simple Solidity coding. You will fully implement the change price function yourself. So it really is not that heavy of a project. The goal is just for you to understand all the different parts of this contract, from the utility functions to the actual constructor to the global variables that make up the contract state and things like that. So that's the contracts part of it. And then doc is fine, migrations is fine. You can read about that in the truffle stuff. Test has all of our tests in here, JavaScript tests. So these are actual front end tests. you can they're almost like integration tests, except it doesn't handle the button clicking side. So in client, we've actually made a full front end for you all that you'll be running for the project, and you'll go into source and yeah, I mean app.js has all the Web3 in it. So yeah, Web3, all these functions, add loot, like you'll look at these functions and try to understand what's going on. Quite a lot of stuff going on. It took as long to do the front end as it did to take the back end, so don't underestimate it. Um, there should be, it's not showing up somehow, but the biggest thing to note is that there should be a contracts folder here in source. Um, and what you'll have to do is once you compile the contracts, they'll go into build as a JSON object. So they're not here right now because you haven't compiled anything in this project, but the way that Web3 works is that it uses the application blockchain interface, which is a JSON object. And that JSON object is created when you compile the contract. So you go in here and you say truffle, you do your coding in Solidity. In the main folder, you say truffle compile, and then it'll end up in build. You actually, in this specific repo, have to copy and paste the JSON that ends up in build. You have to copy that and paste it into the client source contracts. And that's how the front end will be able to see the contract JSON. And that's its API. That's how it calls the smart contract and things like that. But other than that, there's nothing too crazy about the project. This document will have everything you need. So it should be fun. Should be just a small, light exercise. I don't foresee it taking too long. But yeah, cool. So yeah, I can definitely stop it here, or I can give you a small survey of things that you could be able to work on as blockchain developers. Really is up to you. I'm just kind of here to answer questions and things like that. So yeah, give me some pointer of what you'd want to see. Okay, well, either way, I'm gonna stop the recording right now, and then we can go from there. Okay, yeah, let's stop the recording, or I'll do it on recording real quick. All right, let's do that. So let's do a quick survey. So would you guys be okay? I'll stop the recording. All right, sorry for those of you who are watching in 2022. Sorry, bye.